And so we can move to the next speaker, who's Ralph Ernstorfer from Berlin. And so Ralph is going to be speaking about concepts for unifying data infrastructure and transparent data analytics in experimental physics. So the word is yours. So we see your screen, Ralph. So now you can just speak.
All right, excellent. Let me just get the right windows back here. All right, so thank you very much for the introduction. Thank you very much for the opportunity to present our work, which is, I will take you down sort of to the street fighter level now after the very generic introduction to the FAIR principles of data management. I will take you to the perspective of kind of a practitioner from the field of condensed matter physics. I'm experimentalist. And I will discuss kind of the challenges we face and have been facing and are still facing, and our ideas to mitigate them in view of making a community and experimental technique fair, which as of today has made very little progress along these lines. I will discuss this on the basis of one specific technique, which is photoelectron spectroscopy, but I think the basic principles I will be touching on are pretty much generic and apply to pretty much any experimental technique that is driven by individual labs rather than large-scale facilities. The key people involved in this endeavor here are Tommaso Pincelli, Patrick Young, and Laurens Rettig, and the key funding sources for this are the Max Planck Society and the European Union. So let me start with a slight historic perspective. So as Luis said, the basic idea of open research data is much older than the FAIR principles. It definitely dates back to the previous century, but a very strong political statement I found is from 2004, which is an OECD declaration, which essentially suggests that research data that is performed with taxpayers' money should be open, with kind of the main goals to enhance the quality and productivity of science. So specifically, what the general public expects from this development is that we see an advancement of the scientific research in general, that we improve the training of researchers, especially also across boundaries and borders, and that we maximize the value of the data that is collected from a given investment, that we sort of reach out wealthy countries that can afford expensive instrumentation, provides a basis for developing countries to participate in the research data that is produced. And overall, of course, a key goal is that the quality of the research improves. There's some concerns, of course, that need to be taken into account. For individuals, it's the protection of intellectual properties, and sort of for larger bodies or nations, it relates to security issues, primarily in privacy issues. So that's the political boundary condition. The question is, where are we in that terms, almost 20 years later after this declaration? The answer is, it very much depends in which field you work in. Let me make an example. So as I said, I'm a condensed matter physicist, and probably the two most basic properties of a material are the arrangement of the atoms and the arrangement of the electrons in the crystal. So if we first look at the information you can get about the atomic structure of a material, if you type in crystal structure database into your favorite search engine, you find many results. Of course, there's not as many databases, but there is plenty. If you do the same thing for electronic structure database, you still find many results, but there's a key difference. The atomic structure is based what databases is based on experimental data, whereas essentially all of this is based on computational data on the electronic structure of a material. And if you sort of modify your search and explicitly add experimental, you will find only an abstract to a talk I gave some time ago. So essentially there is no, there's a huge discrepancy between experimental open data, only if you sort of consider very different aspects of material, the atomic structure or the electronic structure. So why is that? So we have the strong political incentives to support open and enforce open access and open research data, but it hasn't happened in all communities. So the European Union is a key driving force in sort of pushing open access. And on the German national level, we also now have a big initiative, the FAIR-DI initiative, that supports this with substantial amounts of funding. But I think the key question we have to ask is not what is policy or the public trying to push us to, but why should an individual researcher participate in this? What are the incentives for an individual to participate in making his or her research data public and open? What's in for me or them? So key motivation could be that you're forced to, and as I mentioned, there is major funding agencies that follow that route. But of course, we don't like doing things because we're forced to. So let's look at kind of the positive effects from that. So why are you benefiting from participating in an open research data initiative? If you participate, you demonstrate maximal openness and transparency in the research you do and how you do it. And on the midterm, I'm convinced that this will lead to improved credibility. In general, I think it's fair to state that any experimental researcher only makes fractional use of the information content of the data collected. So by sharing your data, you make it accessible to other approaches, other communities, and other expertise. This will only fly or sort of be an incentive if you will get credit for that. So what has to happen is that individuals need to be able to demonstrate that they have a scientific track record and that this is appreciated in the sense of a personal advantage in your career path, for instance. Then a big motivation is that if you turn a lab effort into a community effort, of course, you will share your procedures, you will share your data, but this is not a one-way road, but that eventually you will also benefit from development of other labs. Side effect is that it very easily triggers collaborations, and but on the long run, it also eases the exchange of researchers, of people. And then the final point is that, in fact, we have been responsible for proper data stewardship for a very long time. So everybody in Germany, at least, has to sign that she obeys the rules of good scientific practice, which in essence requires that everything you do, your research, is reproducible and can be reproduced for 10 years and more. I would claim that this rule is existing on paper, and many groups would fail if they would be forced to demonstrate this. So overall, the hope is that we do better science in the sense that we make the process that we call science, which is extracting knowledge from data, fully transparent, reproducible, and transferable. So now, what are the challenges in doing this, and why in my community at least, we haven't made much progress along these directions. So let me start with kind of one of my favorite experimental techniques, which is angle result for the emission spectroscopy. No worries, I won't explain any details, but it's important to understand the basic aspects of such an experiment. So there's a sample, it's illuminated by light. The light kicks out electrons and the electrons are detected. The detector then records basic aspects, the energy and an angle of emission of the electron. And this is what we traditionally call the data. And this is, many people refer to this as a snapshot of the electronic structure of a material. But besides this data, there's a lot of additional so-called metadata. And it's natural to group this along the basic components of such an experiment. So there's metadata associated with the detector. This can be 2, 3, or even 4-dimensional data. There's data associated with the light that is used to do this experiment. There's data associated with the sample, the parameters during the measurement, like temperature, but also the history and other characterization that has been done. And importantly, there's also data related to the act of performing the experiment, which is sort of soft metadata, but which is incredibly important. So a key message I want to get across is that if you want to achieve fair data management, we need to treat all this data on the very same level. And I will explain in the coming slides what I mean with this. The requirement to achieve this is that we have automated access to pretty much all these instrument parameters, this metadata, and that we need to improve our recording of this data and the optimization of the entire experiment tremendously. And one step, and a key step, is that the use of electronic lab notebooks need to improve in my community, at least, tremendously. And there we'll learn more about this in the course of this this workshop. So let me show you what the challenges are based on a real example. So in this experiment, what you record is a stream of single electrons, and every electron has a couple of parameters. So a position on the detector, time of flight, some other parameters characterizing the experiment. And we record billions of these electrons per hour. And this is actually what we call the raw data. This raw data is essentially not accessible. In order to make it accessible, it needs to be transformed. So it needs to be processed, and it needs to be converted from a stream of single events into some volumetric data, where the axis of what one looks at is already a subjective choice of the experimentalist, depending on which kind of information that person would like to retrieve from that data. But this process here is very complex. Depends on the experiment, of course, but in general, this is a very complex process. It even is iterative in some experiments, and it's very it's a very individual process. So it depends on the hardware, but in many experiments, it even depends on the details of a single acquisition. So it changes between different experiments of the same with the same machinery. And it's a key process to arrive at what most people would call the raw data. So one should be aware that raw data is not the same as raw data. If you use a different ARPIS technique from the same community, you will have a similar workflow arriving at this point, but the details can be completely different. So such a data set is kind of the common base of a given technique, of a given community, the ARPIS community. So one has to agree on how this data should look like. And an important aspect is that this already includes a tremendous reduction in the data size, which means that you also lose information in that process. And this is important to realize. So this data will be combined with the type of metadata I have shown before. And if you combine this and put this on an open repository like Zenodo, one could think, okay, we're done. So let's check. The data will be findable and accessible. This we achieve. The reusability of the data will be rather limited. I explain why. I would claim that it's close to not interoperable. And an additional important aspect I would like to discuss is the data itself arriving at this point, what the raw data itself is not necessarily reproducible. So this process here, if this is not properly documented, we don't have a reproducible workflow, even if the data acquisition itself is highly reproducible. So if you come back to the FAIR principles, what do we need to do? The aspect of making the data findable, that's a fairly easy one. So this can be easily achieved right now. Make it accessible. This is also very simple and largely in the responsibility of the people operating data repositories. To make it interoperable, this is probably the toughest one, because what we need for that is we need to agree, we as a specific community, on a certain language on how we describe the data. To make it reusable, of course, this aspect is also very important. And as I said before, it needs to be done in an entire community, so in a specific domain of experimental physics. In this case, that there need to be a community standard. And to make things reproducible, we need to add transparency to our workflows. So from that, there arise several key challenges on our way to achieve really fair data publishing. And I will discuss what I consider the key aspects. So the first one is the reproducible data processing workflow. So I'm talking about this circle from going from really the true raw data to what the community would consider the raw data. In our example, this is really, it's a complex workflow where sort of you have the data from the machine going through a sequence of different algorithms and then arrive at the data where the data analysis would only start. What we do to achieve this is we essentially take the effort and write papers about each individual steps and share the code in a repository on GitHub. But we have been starting doing this only 2 years ago, and we are still only one of a few groups that do this, and for the vast majority of groups in my community, this process here is not transparent. I'm not saying that they do, they're making mistakes there. It's just not reproducible for people outside these groups. A second challenge in achieving interoperability is to achieve a unified metadata structure. So we have the problem that ARPIS it's a very broad technique, but there's different flavors of this. So there's kind of the conventional ARPIS, which records photo emission intensity, function of energy and momentum of the electrons. Then there's spin resolved ARPIS, where additionally the spin state of the electron is recorded. There's time resolved ARPIS, where this changes over time and movies are taken of the electronic structure. There's spatially resolved ARPIS, and there is many more techniques, and for sure there will also be new techniques being developed in the future. As of today, these are different sub-communities, and somebody doing spin resolved ARPIS thinks she has very different data structure compared to somebody doing normal ARPIS or time resolved ARPIS. So how can we bring this together and really merge this into a single community? One idea is, as I mentioned before, that we give up this distinction between data and metadata. So if we consider our signal as photoemission intensity in a high-dimensional parameter space, where some of the parameters are kind of the classical dimensions that are recorded and resolved by our detector, and all the other parameters are associated or historically called metadata, sort of, for instance, parameters characterizing the photons used to do the experiment, the geometry of the experiment, intrinsic parameters of the sample. And if we sort of give up this distinction of data and metadata and merge it into a single high-dimensional parameter space, then we have a formalism that in principle can cover all different RPES techniques. So, and I discussed this now for my specific technique of photo emission, but this basic idea, which is very trivial in nature, can be transferred to many other communities, for instance, optical spectroscopy, which is also a very wide and perceived as very diverse experimental technique. So how can we do this? We have made a suggestion on how to achieve this. And the key ingredient is that one reaches out to the community and agrees on a dictionary. So essentially, this contains all the terms and words that are relevant for any of the RPES techniques. One has to agree that there's only one term for a given thing, like a photon energy, that it's called between the different techniques the same way. And then the sub-communities, the subdomains, have to agree on which of these parameters here are really important and essential for a given flavor of the RPES experiment that they are performing. So this is called an application definition. And we're thinking of doing this here in the hierarchical structure of the Nexus data format. And with these ingredients, we can then merge what is traditionally called the raw data and the metadata, and have to develop a parser. This is specific for every lab, every experiment, but you only have to do this once. And this would parse then the data into this hierarchical structure. And then we have essentially a merged data metadata set, which then, after checking the compatibility with a database, could be uploaded and be a very structured data set and be essentially have the same structure for the entire community. So an example would be that we would use this natural distinction that an experiment is usually combined from different aspects like sample, detector, light source, and so on. Use this block-like structure, and then each application would choose which of the blocks are important, and again, which parameters in which block are really important, and agrees on such application definitions. But it's really important that this is not a decision made by an individual research group, but that the community would agree on such a convention. And this is probably the biggest challenge in this, and especially for where we are with this right now. So how can you spread the word about this, spread the idea, and how can this be turned from the effort of an individual group to a community effort? So what we try to do is we try to really properly describe these ideas on a web page, and we try to reach out through workshops, conferences, and really in-person meetings. If you achieve this, I think we're still not done with the aspect of interoperability. Because if you look at the definition, what that actually means is that it's the ability of data or tools from non-cooperating resources to integrate or work together, which means that different aspects exchange and make use of information. So this, an example for my case would be that computational data and tools existing in the world of computational research would be applicable to and be made comparable to experimental data on the electronic structure. So if you look at this on the experimental side, we have large high-dimensional data sets where an individual data set is on the level of 10 gigabytes. And the information content that one would like to retrieve from that is linked to really very complex and basic properties of a material. So it's a very rich spectroscopic signal. At the same time, it's very complex. And retrieving this type of microscopic information on the electronic structure of a material from this data, this is current research. So this is currently done by hand, by individual researchers, and there is no generalized technique, because this process of kind of knowledge extraction from this and expressing the knowledge in terms of, well, microscopic properties, this is done on a very individual level, depending on the problem at hand, which scientific questions would want to be answered, which class of material that is. So this is extremely diverse and extremely non-uniform. So really achieving interoperability at the current state appears rather unfeasible. In order to make steps in this direction is that we need tools to reduce the complexity and also the size of what we consider the raw data. And we need tools that don't aim to kind of retrieve all the information that is possible in this data set, but take a first step and extract kind of basic knowledge from such complex data sets. And basic knowledge, for instance, we talk about the electronic structure. Basic knowledge would be what is the dispersion of these bands of the electrons in the crystal. And I want to show you some examples of what we have been doing in this direction. So the general goal is to develop data analytics tools that lead to a reduction of the size of the data and would extract the essence of a data set, but this is a subjective choice, what you consider to be the essence, that then would allow that you compare experimental data with computational data, and eventually then allow to go one step further and start really building a database, an experimental electronic structure database, based on sort of not the full complexity of the data, but what a group or a community would define as an essential information content of this data. So, an example, what we have been trying to do is, if you have such an image of the electronic structure, the people with a physics background know that these are dispersing bands describing the states of the electrons in that material. But it's much more complex compared to a computed band structure. So what we have been demonstrating is that with a chain of pre-processing steps, one gets this data set ready to apply some machine learning techniques. So this is a rather simple probabilistic machine learning approach where we feed this data through. This approach is sort of preconditioned by computational data, which is publicly available in databases already. And after some post-processing, one can retrieve the shape and energetic position of essentially all the bands of the electrons in that specific material. So the result of this procedure here then is essentially such a representation of the bands of the electrons. And this can be expressed in a polynomial basis because this material has a hexagonal symmetry. So here you see kind of the topology of all 14 bands. They agree rather well with theory. But the key point is that now we have a representation of what most people would call the key information, the band structure of that material, and it can be expressed in a polynomial basis. The consequence is that we have reduced this volumetric data set by more than 4 orders of magnitude, from gigabytes to less than megabyte data, with sort of the difference in the representation of the band structure, if you're only interested in that, being less than 1%. So now with this, we can, what I would consider the last challenge, and take the step from putting the data onto a repository and take the step to build an encyclopedia. And what we need to do for achieving this is we need to develop advanced data analytics that sort of extract key information. We need to achieve data reduction to a level that a large number of people is comfortable handling. We also need to develop tools that allow to inspect the data, because in general we talk about high-dimensional data, and most humans still kind of only connect to things if you can visualize it. And we then can start to link experimental information on electronic structure with calculated databases of the electronic structure. All right, and what I've discussed is essentially what I consider the key missing steps as of today in order to achieve this. And we sort of teamed up with other people, and we participate in the FAIR-MOD consortium, where angle resolved four-dimensional spectroscopy is sort of one of the experimental techniques or communities that is present already from the start, and where the basic concepts to sort of making our data management fair are meant to be implemented. We closely work together with other experimental techniques, and you will learn about some of these in this workshop. For instance, electron microscopy by Christoph Koch. But also we reach out to other spectroscopic techniques, optical spectroscopy, for instance, because I'm convinced that they face the very same challenges as we do. And then, of course, the big benefit of doing this will be if we start leaving our domain of experimental research and really make our data accessible, interoperable for other communities, especially, of course, to theory and computational research. So what I have discussed, we really need, as a community, make progress on a common metadata standard. We need to make our data workflows transparent, and we need to share them. We need to make it a community effort, and I think this is a very important aspect to create incentives for other groups and people to join, because this is in practice a huge effort. And if you can benefit from what others have been doing in the past, this is a very big incentive to join the club. And then, of course, the key goal is to establish an encyclopedia. And to achieve this, one needs to adopt concepts that sort of bring together very specific experimental techniques that largely at this point still think, okay, they are isolated, they are singular, and their data structure doesn't exist anywhere else. So one needs to think of data structure concepts that are unifying and sort of bring many groups, subdomains together and make them realize they're actually, in fact, a single domain. Thank you very much for your attention.
Thank you very much, Ralph. So I see in the chat there is already a question by Luca. So Luca, you can unmute yourself and ask the question.
Okay, can you hear me?
Yes, we can.
I thought you would read. So my question, yeah, thanks Ralph for a very nice overview, and a kind of provocative assessment. So my point is about this kind of so the interoperability point that you have made. And I think it's more towards reusability. So before talking to the to the theorists, let's say, so comparing so using the metadata that you have stored for the experiment and see if you have a connection with the theory. What about experiment to experiment, even with the same device, say different vendors, different groups? So if you have different settings, how do you compare data so that you can use data on different samples in the same kind of scientific project? So without redoing by yourself, because at the end, you don't know what to do with data done by obtained by others.
Yeah, this is a very good question. And I would say from my perspective, it's equally complicated to compare our data with computational data compared to experimental data from another group. The level at which comparison happens now is on the very far end of data after all the data analytics that has been applied. I'm not talking about kind of this pre-processing workflow that would bring us to what we consider the raw data. I'm really talking about the far end when data is further analyzed and sort of a key aspect is extracted. At this point, different experimental groups would start comparing. It's essentially non-existent that one group, let's say us, with our workflow of doing data analysis would feed in data from another group, because at the current stage, it would be such an effort to make, I mean, sort of, Luis mentioned 80% of the time, it would be very similar. It would be such an effort to convert the data to make it usable for our algorithms that this in practice is not happening. So it's at the current state, this is close to zero.
Okay, we have. Sorry, just to follow up. No, do you think it is an effort worth taking to kind of try and really speak the data together? Because of course it is great that you have the data if you want, and then you can check and reproduce. But what about having a translation between one group to the other to make it short?
Well, I mean, sort of what I discussed here, I guess I was mostly motivating it in terms of making it comparable to computational data. But sort of what I presented here as kind of making it unified over the entire community of ARPAs, this would exactly allow this. So it wouldn't make a distinction between other experimental data or computational data. If we achieve kind of this common nexus-based metadata standard or data structure in general, then you can do this. Then you can also compare different experimental techniques. But it's sort of it's the same. The road to achieve that is very much the same. And yeah, we at the current stage, there's no advantage in sort of, or we don't have made further progress in comparing with other experimental data compared to computational data. With other experimental techniques like optical spectroscopy, this might be a slightly different. But in our field of photoemission spectroscopy, I think that's the case. The only comparability you have is if instruments at large-scale facilities are used, where people bring their sample, take data with the very same machinery, and they go home with sort of data in a certain structure. It doesn't comply with all requirements I've been discussing, but then different groups have the same type of data, and this can be compared. But this is only a small fraction, I would say, of the data that is collected in the entire community.
Okay, so we have a few questions here. So the first one is by Stefan Cottenier.
My question is about your challenges 1 and 2 when you're at the level where you are still operating on the raw data or close to the raw data. So you develop tools within your group that you hope to generalize in the same or in a modified form to an entire experimental community. And that is a hard psychological effort because people will either be ignoring you or they will develop their own tools. And in the end, you will have then many competing tools. But in an experimental community, you have something extra that we in the computational community do not have. You have the vendors of equipment. So I wonder, would it be an option to develop, even in your own group, something that works and then offer it for free to all the vendors of detectors and convince them to implement that in their native analysis software? And in that way, suddenly everybody in that community that buys a new detector will have the procedures available. So that makes it super easy, and maybe in this way the idea spreads. So I don't know whether this is anyhow realistic. That is my question to you.
This is an excellent question. So the situation in my community is there's a handful of vendors. It's sort of the key thing is the electron spectrometers. And we have, although it's very few, we have kind of all the extremes from sort of one vendor being very transparent and sort of very eager to sort of adopt developments of the community. Another vendor being very secretive about the details of the instrument because I think they fear that people could do back engineering. For instance, if they make sort of this loop here, if they make this loop transparent, then of course you can learn about the instrument itself, and if this is protected, then well, there's certain danger. I can understand this. So in my small community, we have all of that, and we're just at the stage to sort of reach out to them and essentially make an offer that they become an active part of this thing. So I would even not say, please adopt what we developed. I would get them on board like all the other research groups as well, and sort of participate and sort of share their ideas as well as concerns, and be part of kind of the active community shaping this. This is our current strategy, and I would expect that some companies adopt this offer and accept this offer, and others not. And then we'll see how things develop. I feel that in 5 to 10 years from now, people making a decision on which instrument to purchase, what I've been discussing will be an important aspect in the decision-making process. But maybe this is too much wishful thinking.
Okay, we have time for a short question here by Michiel van Zetten.
Thank you, very interesting. I just wanted to kind of put one more layer of complexity maybe. I think in this very complex data, right? Having FAIR data is one thing, right? But if I want to search like a database for something, I would like to search for something like, well, trivial thing would be a gap of something or some very specific feature. What is your thought about this, about kind of basically this downstream analysis, how to kind of turn language effectively completely into something that can then be searched on such a complex database? Yes,
very good point. So I think that this is a key aspect of kind of this development here. So if you have such a representation of the data, so this is essentially the projection of the data onto a polynomial basis, let's put it like this. And the size of this is sort of kilobytes. And of course, now this contains, for instance, basic properties like dispersion, gaps between the bands, and so on. I think that's a good example for the reduction we have to do at the current stage, meaning for the next couple of years, to sort of data of that size and complexity is of interest to a wide community. The raw data, not. And I think it's we'll see then how quick the development will be for really truly advanced data analytics. And I think this won't happen without really advanced machine learning approaches, much more complex than most data mining approaches used right now in material science, to sort of make use really of the full beauty of the data set, the full information content. But I think as of today, this is kind of the level we are talking and kind of you were thinking of right now, I think.
Thank you very much, Ralph. So I think we have to move to the next host. So thanks again from everyone here and from all the audience.